Let me start with a question. Imagine you're running a large-scale fuzzing infrastructure, something like OSS Fuzz at Google. You've been fuzzing a project continuously for months. You've already found hundreds of bugs, and developers have fixed them. The code base is now relatively stable. Now, here's the question. Where do you think the next bug will come from? From code that's already been fuzzed thousands or maybe even millions of times? Or from code that was committed yesterday? Take a moment and actually think about that. Intuitively, most of us expect that new code is riskier, but intuition alone isn't enough in system security. So the authors of this paper did something very interesting. They analyzed over 23,000 fuzzer-generated reports from OSS Fuzz, and what they discovered was quite surprising. 77% of those bugs were regressions. That means the bug did not exist in earlier versions of the program, rather it was introduced by a specific commit. In other words, the majority of bugs discovered by fuzzers were caused by recent code changes. But it gets even more extreme. When the authors looked specifically at mature projects that had already hundreds of bugs discovered, they found that the probability that the next bug was a regression went above 90%. So, once a project has been fuzzed for a long time, almost every newly discovered bug is introduced by new code. Let's pause and think about the implication. If almost all new bugs come from recent commits, why are fuzzers spending equal efforts testing code that hasn't changed in years? Why are we wasting compute power exploring stable code paths that have already been heavily tested? That question is the core motivation behind this paper. The authors propose a technique called Regression Greybox Fuzzing, or RGF. Today, I'll walk you through first the empirical motivation behind the work, next, why existing fuzzing approaches are not sufficient, third, the technical design of Regression Greybox Fuzzing, fourth, the experimental evaluation, and finally, what this means for system security and fuzzing infrastructure going forward. So, before we dive into the contribution of the paper, we need to briefly review how modern fuzzing works. Most of you are probably familiar with AFL, the American Fuzzy Lop Fuzzer, but let's step back and categorize fuzzing approaches. There are three main types of fuzzing: black box fuzzing, white box fuzzing, and gray box fuzzing. Black box fuzzing is the simplest. The fuzzer generates random inputs and feeds them into the program. There is no internal knowledge of the program structure. It's extremely fast, but also completely blind. White box fuzzing is the opposite. It uses symbolic execution and constraint solving to reason about program paths. This allows it to precisely generate inputs that reach specific branches. However, this approach is computationally very expensive and does not scale well. Gray box fuzzing sits between these two extremes. It instruments the program lightly to collect coverage feedback. That means the fuzzer can see which code paths were executed. This allows the fuzzer to guide its search without requiring expensive symbolic analysis. Now, let's look more closely at how AFL works. AFL begins with a seed corpus, which is a collection of valid inputs. The fuzzer mutates these inputs. It executes the mutated inputs against the target program. Then, it records which part of the program were executed. If the mutated input causes the program to explore a new execution path, that input is considered interesting. It is added to the corpus. Then, AFL will generate additional mutations starting from that input. Over time, this creates a feedback loop. Inputs that lead to deeper exploration of the program get expanded further. Inputs that lead nowhere are discarded. This approach is extremely effective in practice. Modern fuzzers have discovered thousands of vulnerabilities in widely used software. However, there is an important limitation. Greybox fuzzers primarily use coverage as the guiding signal. Coverage answers the question, did this input execute new code? But coverage does not answer another important question, how risky is the code that was executed? Coverage treats all code equally. From the fuzzer's perspective, a branch in code written yesterday is the same as a branch written 10 years ago. But from a security standpoint, that assumption may not be realistic. New code tends to be more error-prone, and that observation is exactly what motivates the work in this paper. The authors begin by studying real-world fuzzing data. Instead of immediately proposing a new algorithm, they first ask a simple question. What kinds of bugs do fuzzers actually find? They analyze 23,000 bug reports from OSS Fuzz. These reports span 376 open source projects over a period of 5 years. OSS Fuzz is a particularly useful dataset because it continuously fuzzes many widely used open source programs. When a crash occurs, OSS Fuzz performs delta debugging to determine which commit introduced the bug. This allows the authors to determine whether a bug was an existing bug that had already been present or a regression introduced by a recent change. They define a regression bug as a bug for which a specific bug-introducing commit can be identified. Now, here are the key findings. Across all projects in the dataset, 77.2% of the bugs were regressions. That means the majority of bugs discovered by fuzzers were introduced by new commits. But the authors go further. They analyze how bug discovery evolves over time. When a project is first added to OSS Fuzz, there is a burst of bug discoveries, about 2.5 bugs per day. This makes sense. The fuzzer quickly discovers shallow bugs that have never been tested before. These might include invalid memory accesses, missing boundary checks, rarely executed error paths, but after this initial burst, the bug discovery rate drops. However, it does not drop to 0. Instead, it stabilizes at around 3 to 4 bugs per week. Now, why does this happen? Because developers continue modifying the software. Every new commit introduces the possibility of new bugs. The authors then observe something particularly important. As the number of discovered bugs increases, the probability that the next bug is a regression increases dramatically. The first bug in a project might only have about a 20% chance of being a regression. But by the time the 1,000th bug is discovered, the probability that it is a regression exceeds 99%. In other words, once a project becomes mature, almost every bug discovered by fuzzing is caused by new code. Now think about the implications. If the fuzzers continue spending equal effort on old code and new code, they are wasting computational resources exploring code that is unlikely to produce new bugs. This inefficiency is the core problem the authors aim to solve. At this point, one possible solution might seem obvious. Why not just fuzz the most recent commit? In fact, previous work has explored this idea. Tools like AFL Go perform something called directed fuzzing. Directed fuzzing attempts to guide the fuzzer towards specific target locations in the program. These targets might be functions that were recently modified. However, this approach has several limitations. Software evolution is not isolated. Bugs often span multiple commits. For example, consider the following scenario. In one commit, a developer introduces an integer overflow, but the overflow does not immediately cause a crash. Later, in a second commit, another developer adds a memory access that uses the overflowed value. Now the program crashes. If we only fuzz the second commit, we may miss the original overflow introduced earlier. Additionally, CI pipelines typically limit the amount of time allocated to fuzzing. Developers cannot realistically run 24-hour fuzzing sessions for every individual commit, and targeting every commit individually would be computationally expensive. Instead of focusing on one commit at a time, the authors propose a different approach: fuzz all code simultaneously, but prioritize code that has changed recently or frequently. This approach allows the fuzzer to remain broad in its exploration while still focusing more effort on risky code. This concept is called history-aware fuzzing. Regression Greybox fuzzing modifies AFL in three ways. 1. Code history instrumentation. 2. A simulated annealing power schedule. And 3. Byte level power scheduling using ant colony optimization. First, the fuzzer incorporates information about the history of the codebase. At compile time, the system instruments every basic block. For each basic block, the system computes two values: age and churn. Age represents how recently the code was modified. Churn represents how frequently the code has been modified. To compute these metrics, the system uses git history. Git blame identifies when a line of code was last modified. And that looks something like this, which you guys have already seen. Git revlist can count the number of commits affecting a file. Diff analysis can identify how frequently a block has changed. These signals help estimate how risky a piece of code might be. Now consider why these signals might correlate with bugs. Age captures recency. Code written recently has not been extensively tested. Older code, on the other hand, has likely been exercised many times in production environments. Churn captures instability. Code that changes frequently may represent complex or evolving functionality. Frequent changes increase the chance that developers accidentally introduce inconsistencies. For example, a function that has been modified multiple times across recent commits may contain partially fixed bugs or new logic errors. By combining age and churn, the system can estimate which part of the program are statistically more likely to contain defects. However, there is an additional challenge. Most code in mature software projects is stable. If we simply average age values across all executed basic blocks, the signal from recently modified blocks becomes very small. To address this, the authors amplify the signal. They transform the metric as follows. Age becomes the inverse of age. Churn becomes the logarithm of churn. These transformations emphasize recent changes while smoothing large churn values. During execution, the fuzzer aggregates these values to produce a fitness score for each input. This score reflects how strongly the input exercises recently changed or unstable code. Next, the authors modify AFL's power schedule. The challenge here is balancing two competing goals: exploration and exploitation. Exploration means searching new areas of the program. Exploitation means focusing on code that appears risky. If the fuzzer focuses too aggressively on recent code, it might miss bugs slightly outside that region. If it explores too broadly, it loses the benefits of regression awareness. To solve this problem, the authors use simulated annealing. Simulated annealing is an optimization technique inspired by the cooling of metals. At high temperatures, atoms move freely. As temperatures decrease, the structures gradually stabilize. Similarly, the fuzzer begins with a more exploratory strategy. Over time, it gradually focuses more strongly on seeds that exercise risky code. The result is a smooth transition from exploration to exploitation, as you can see on this annealing strategy graph. Importantly, the authors do not replace AFL's power schedule, they simply scale it. This makes the system easier to integrate into existing fuzzing infrastructure. The final component operates at the byte level. Most bytes in an input do not affect program behavior. Mutating those bytes repeatedly wastes time. Instead of using expensive dynamic taint tracking, the authors apply ant colony optimization. The idea comes from the behavior of ants searching for foods. Ants leave pheromone trails along successful paths. Over time, pheromones evaporate. Paths that consistently lead to food become reinforced. The authors apply a similar idea to input mutation. When a mutation improves the fitness score, the system increases the score of the mutated bytes. Over time, these scores decay. This prevents early random successes from permanently biasing the research. When selecting bytes to mutate, the system samples according to these learned probabilities. This allows the fuzzer to focus mutation efforts on the parts of the input that matter most. To make this efficient, the system uses the alias method, which enables constant time weighted sampling. The result is a fuzzer that prioritizes both promising inputs and promising bytes within those inputs. And here you can see a graph of energy scaling in RGF, and you can see as seed fitness increases, we have a correlation with the energy amplifier. And then of course the byte level learning. It identifies influential input bytes, and it adapts mutation probabilities. So, the experimental setup. The authors evaluate their system using 15 open source C programs. Oh, and sorry, there was one more slide for the ant colony optimization, which again is inspired by how ants share that they have found food by reinforcing paths that consistently lead to food. In this case, reinforcing paths that consistently lead to bugs or new discoveries. So, the experimental setup. The authors evaluate their system using 15 open source C programs, 20 regression bugs, over 3 CPU years of compute time, and 20 trials per experiment. They compare several configurations: standard AFL, AFL churn, age-only prioritization, churn-only prioritization. They also carefully choose program versions that existed before the bug was fixed, ensuring that their approach does not receive unfair advantage. All experiments are reproducible through the fuzz bench framework, which adds credibility to their evaluation. Now, for the results. The main result is that AFL churn discovers regression bugs approximately 1.5 times faster on average. In some cases, the improvement is dramatic. For example, the time required to discover a particular crash dropped from 17 hours to 9 hours. The authors also observe improvements in consistency. More trials result in crashes. Crash stack traces often involve recently modified code, validating the regression hypothesis. Interestingly, neither age nor churn alone consistently dominates. Some programs benefit more from age-based prioritization. Others benefit more from churn-based prioritization. Combining both signals produces the most consistent performance. Now for a critical analysis. The strengths of this paper include strong empirical motivation, lightweight integration into AFL, no expensive runtime analysis, reproducible experiments, and consistent performance improvements. However, there are limitations. The evaluation focuses primarily on C programs. The approach depends on high-quality Git history. It does not incorporate semantic complexity or static vulnerability predictors. And future work could combine history signals with complexity matrix or machine learning based vulnerability prediction. And for broader impacts, this paper suggests a shift in fuzzing philosophy. Traditional fuzzing assumes all code coverage is equally valuable. This paper argues that code history is a meaningful risk signal. In modern DevOps environments, software evolves rapidly. Continuous integration and deployment pipelines introduce frequent changes. Regression-aware fuzzing aligns naturally with this workflow. For example, CI systems could automatically prioritize fuzzing newly modified components. This would allow fuzzing infrastructure to adapt dynamically as software evolves. And now for the conclusion. To summarize, 77% of fuzzer discovered bugs are regressions. In mature projects, almost every new bug is introduced by recent commits. Traditional fuzzing treats all code equally, which wastes computational effort. Regression Greybox fuzzing, or RGF again, introduces history awareness using code history instrumentation, simulated annealing power scheduling, and byte-level mutation learning. This approach finds regression bugs faster and more consistently. So I'll leave you with one final question. If most new security vulnerabilities are introduced by new commits, should fuzzers become history aware by default? So, that is the central takeaway of this paper, and hopefully you'll go read it yourself as well.